Quien va a presentar ahora es Rafael Ferraz. Su trabajo se llama Power Flow and Fault Analysis Using Graph Theory. Pertenece al Postgraduate Program in Electrical Engineering de la Federal University of Espírito Santo en Vitória, Brasil. Así que, bueno, si Rafael está por ahí, te damos la bienvenida y el tiempo es tuyo, puedes comenzar cuando quieras.
Okay. So, good morning, everyone. The title of my paper, it is Power Flow and Fault Analysis Using Graph Theory. I am a co-author, my name is Rafael Ferraz, and the other authors are Renato Ferraz, Augusto Rueda-Medina, and Marcia Paiva. This paper was developed in the Federal University of Espírito Santo, UFS, in Vitória, Brazil. The introduction. Nowadays, main distributed energy resource, the DER, have been integrated in the distribution system. As a result, the problems...
Un segundito. The next slide, we only see the first. Okay.
Now it's okay?
Okay.
So, as a result, the problems regarding the power system operation and planning have become more evident. In most cases, the power flow and short-circuit algorithms are necessary to deal with these problems. For this reason, it is necessary to implement an algorithm which takes the phase unbalance in account to solve the power flow of the distribution system and to reach the short-circuit currents. The purpose of this paper. In this paper, some graph theory concepts were used...
Could you, the next one, the next presentation? Yeah.
Let me share again. Is that okay now?
Okay.
So the purpose of this paper, in this paper, some graph theory concepts were used to improve the BFS algorithm, that is a backward-forward sweep, and to assist the short-circuit current calculations. The distribution system are modeled as graph, and using the single-source shorted path Dijkstra algorithm, it is possible to automate some steps of the power flow and fault analysis. The contributions of this paper. The first one, the proposed algorithm used the graph concepts to automatically define the sequence for calculate the current of each branch and the voltage of each node in the BFS, that is the backward-forward sweep. The second one, regarding the fault analysis, the computation of the equivalent impedance from the source to the faulted node becomes an automated process taking the graph theory concepts in account. And the algorithm presents a substantially low computational effort, as we can see later. Here we have some graph theory concepts. The first one, a graph G, is denoted by a finite non-empty set of vertices V and a set of edges E. The degree of a vertex V is the number of edges incident to V. A vertex whose degrees equals to 1 is called a pennant vertex. So the pennant vertex here is the end vertices of a system. A connected graph G is a graph where every two vertices U and V are connected by at least one path. And a path of minimum length between two vertices U and V is called a shorter path. Now we have the flowchart of the power flow algorithm, and we have the flowchart of the short-circuit algorithm. The first one, we have the power flow, where we initialize the input parameters. We use the power injection at each node, the line segment impedance, the nominal voltage of the system, and set of the graph edges. Then we compute the adjacency matrix based on the adjacent vertices, and then we compute the pennant vertex of the graph. And finally, we compute the shorter path between the vertex, which represent the substation, and each pennant vertex. And then we start the backward-forward sweep, where we set the initial voltage of each node, the V0. Then we calculate the three-phase current injection of each node. And then we have the backward sweep, where we calculate the three-phase current of each branch. And we have the forward sweep, where we update the voltage of each node. And finally, we analyze the stop criterion. If it is satisfied, the algorithm ends. If not, we come back to calculate the three-phase current injection of each node, and we have the backward sweep and forward sweep until the stop criterion is satisfied. Now about the flowchart of the short circuit, we will initialize the input parameters. So we use the type of fault, the faulted node, and the short circuit impedance. Moreover, we have the line segment impedance, the nominal voltage of the system, and reset of the graph edges. Then we compute the adjacent matrix based on the adjacent vertices, and then we compute the shorter path between the vertex, which represents the source, and the faulted node. And finally, we compute the equivalent impedance from the source to the faulted node, so we can obtain the faulted current and the voltage. So here we have the faulted voltage, or the faulted current of the phase A, B, and C, and the voltage of A, B, and C, and the phase A, B, and C. And we have the ground voltage. The method used in this paper is able to handle unbalanced systems with mutually coupled phases. In figure 3, it shows a distribution system modeled for a short circuit analysis. So we have the system voltage source, the equivalent system impedance, the substation transformer impedance, and then we have the total line segment impedance. So the IEEE 13, 34, 37, and 123 node test filters were used to evaluate the proposed methodology. So here in figure 4, we have the IEEE node test filter. In figure 5, we have the IEEE 34 node test filter. And here, figure 6, we have the 37 node test filter, and figure 7, we have the 123 node test filter. So now we have the results of the power flow algorithm. As we can see in the first line of graphics, we can see the results related to the voltage of each system, the 13, 34, 37, and 123. And the second line, we have the current of each system. It's important to note that in black, we have the IEEE report results, and in red, we have the results of this proposed algorithm. We can see that the results are very similar. About the node test filter that were used here, the first one, the IEEE 13 node test filter presents high current values since it's highly loaded. Therefore, the voltage regulator is necessary to prevent undervoltage problem. The IEEE 34 node test filter presents light loads and long distance between the nodes, which may cause undervoltage problems when the voltage regulators are disregarded. The IEEE 37 node test filter presents high current values and low distance between the nodes. Therefore, the voltage magnitude does not constantly decrease as far as the node moves away from the substation. And the last one, the IEEE 123 node test filter, the high dimension and the large amount of load cause a substantial voltage drop between the nodes of the system. And here you can see the results of the short circuit algorithm, where you can see, again in black, we have the IEEE report results, and in red, we have the results of the proposed algorithm in this paper. In the first graphic, we have the three-phase fault. The second one, the three-phase to ground fault. The third one, the line-to-ground fault. And then we have line-to-line fault. And finally, the line-to-line to ground fault. Table 1 shows the mean percentage error and the runtime for the power flow and fault analysis. So here, in this table, you can see in the first part, we have the results of MPE and the runtime in seconds of voltage, in this case, MPE, of voltage and current of each system, that we have the 13, 34, 37, and 123, and we have the runtime in seconds. And the second part, we have the results of the MPE of each type of fault, that we have the three-phase to ground, line to ground, line to line, and line to line to ground. And you have the runtime of the algorithm processing. As for the results and discussion, it is possible to notice that the power flow solution obtained through the proposed algorithm is significantly close to the reference values. The same conclusions can be taken from the short-circuit current results, given its substantially low MPE. The low runtime of the proposed method depicted in Table 1 makes its implementation practicable in several problems regarding in electricity sector. The low computational effort is essential mainly in real-time problems, and when the power flow solution and short-circuit current is required several times. And as for the conclusions, regarding the power flow study, it was possible to conclude that the algorithm presents a significantly low computational effort, in addition to preserve the high accuracy of the BFS method, the backward-forward sweep. Therefore, it is possible to avoid the need to order by layers all the nodes of the system, which reduce the possibility of errors. Furthermore, the high accuracy and low computational effort were also observed in the short-circuit current calculation. And moreover, it is important to mention that the algorithm depicted in this paper regarding the power flow and short-circuit analysis are unsuitable for radio systems. Finally, the proposed method presents an important contribution to the electricity sector, since it makes the implementation of the power flow and fault studies easier and has the potential to present good results for real test filters with high dimensions. So thank you, everyone.
Thank you, Rafael. We will wait some minute, 1 minute or maybe two for questions. We are okay with the time, and we could wait maybe 1 minute for questions. Bueno, we have a question. How much was it possible to reduce the time of computation?
And for example, it helps mainly for the reduce the possibility of errors. For example, when we have to calculate the BFS, we have to order by layers, and if we use this method, it can reduce this possibility of errors. So it's important. It helps to organize the code.
Okay. It's possible to see again the last, not the last one, the before the last one slide of your presentation.
Which one?
Before the previous. Okay, yes. Okay, the next one. Your algorithms are only suitable for radial systems, you say.
Yes. When we use, for example, the backward-forward sweep, we need to have the radial system to calculate the voltage and current. So here I put this as a problem of this paper that is just for radial system.
Okay. Maybe we will wait one more minute for one more question. Okay, Rafael, thank you very much.
Okay, thank
for
you.
the presentation, and continue enjoy this Congress.
Thank you.